Hello, this is Saturday, February the 10th, 2024. My study of modular forms have led me to a search of a modular function of level 3 of order unity. And I want to document my work on finding such a function, whether I succeed or not. The starting point was this equation for the zeros and poles of any meromorphic function being invariant under common order 3. And it's just possible to have one of order unity. So I thought, interesting. First, I gathered the knowledge we already had from the section. This guy lying in M4 and this guy lying in M3. So could we combine them, like divide them? This one has a 0 at omega. E4 has a 0 at omega, so that's 3z equals omega. And that lies here. So that's a 0 in its own right. And then this is a 0, of course, because E4 is invariant under S and T, so it has two zeros. This one has 1 0 at naught. So no division is possible here. It won't give a form, it will give a modular function. So that idea didn't work out. Next, I went to the net, I have the address here, and found this. It's very easy to verify that this function is a modular function of level 1 and weight 2. And then the formulas I derived actually have a general form, and it did become something of an industry at the end. So a smart guy would be able to generalize into a general formula, and I would have been able to understand it better had I solved, I don't know the number of the problem that led me to derive all these formulas. If I followed the procedure in the problem itself, then it would have been pretty clear that they all gave never mind. So the formula is not too difficult to understand. I don't understand this, however, what it means exactly. But neither does the guy who asks the question, so let's leave that for the moment. So that means at M2, we have this function. So where is its zeros? Oh, that's obvious. It must have a double 0 at Q. I worked a little on it, and my idea was if we have a 1 of order 2, then maybe we could use the square root to give 1 of order unity. That was the same idea practically that we used with the theta function. So why not try here? So we define E2 and check that it does give the right result. And the function. And then we take minus 2 outside a parenthesis and get 1 plus 12q, etc. And we were interested what might the square root look like. And this is it. And we see all these factors being a multiplum of 6. So that's it. That looks very promising. So let's generalize it, and then we don't want to see these two expressions. And let's run the script. It only ran to, it didn't do that. It appears that I've written the node after the formula. There we go. And I missed a semicolon. So we shouldn't have been seeing all of this. There we go. So Q to third, Q to fourth, Q to seventh, ninth, 12th, 13th, and integer coefficients increasing very slowly. We get to 4 when we reach 100, so that seems like they grow like the logarithm to n. This looks very promising. I believe the next step would be to see if I can find a formula for these coefficients. But what it tells me is that we are on the right track. That was basically what I had to say today. So I had two ideas originally. One was to use these functions and see if we could create the function we needed by operating on these. One idea was, for instance, to square this and then divide, but none of these ideas work. The series are, we simply lack some functions in these spaces. This of course is one-dimensional because they must have a double root at Q, but the others here should be two-dimensional, or maybe this should be three-dimensional, really. Two-dimensional, three-dimensional. And we are missing some guys, but if we find one in M1, then we can create the ones recursively and probably make a full description of the spaces. So that was what I had today. One day has passed. It's Sunday, the February 11th. The challenge was to find a formula for these numbers. You know, going down, up, constant, down. It reminded me a little of the Möbius function. So I said, well, let's fold it with the Möbius function. We have it called mu in Mabel. So that's what I did, and got this sequence. And I wondered what is the formula behind these numbers. It's very positive. It's only 1 and -1, and when the index is divisible by 3, then it's naught. It came out nice. I actually did find a system and a final formula, but the point is that the way to fold is by doing this. That was not the best thing I did. So now I did it correctly, folded it correctly. This of course took some hours, wasted. And look at that. That's just the Legendre symbol n over 3. And that means that the coefficients simply come by adding the Legendre symbol of all the divisors of n. So I computed that, added them, and then subtracted the coefficient to see that we got naught, and we did. That was the work of yesterday, where I was actually able to find the formula for the candidate. So, what are the next steps? One thing we should try to do, I think, is square this and see if I get a nice formula connecting the sum of divisors. It's very likely that it's trivial or gives something quite uninteresting, but I think we should do it just to see what happens. Next, I need to when working with the sums over a lattice, we got an expression with a sum of divisors to QN. So I think I'll have to go backwards and see if this can be written as a sum over a lattice, and then maybe there is a way to work with that. Convergence, of course, seems to be a great problem, but that's the only idea I have presently on how to expand this sum or do something with this sum. Maybe I'll get another idea though. It's now Monday, 13th. I put in the Möbius function here by mistake, so I corrected that. Afterwards, I realized we might change the order of summation. So for each n here, we sum over all powers of q to nth, which gives and I just checked it. That was the next thing. That was actually to make a program computing this. So first we compute q, and then the absolute value of the real part of it. And then we check that it's between naught and unity. And then we find out how far we need to sum. And if that's too large, then we truncate it and print warning. Now I have computed the coefficients in advance here, simply by adding the divisors. That doesn't take long. And then we do the usual computation of a polynomial, minimizing the number of multiplications needed, and testing with f of the imaginary unit 1.0112, and then I check the other formula by adding up to 40. I don't know exactly what was needed. Let's try 20. That gives the same. So not many terms are needed, basically. And then the zero of order 2. No, that should have order 1. That was the known zero for the other function, which had order 2 for the function in M2. So we make a sequence where we make a little circle around naught, and then add that to Q and compute the values. Next we take the argument, and since it's naught as Q, it should go around from naught to 180 once, and that's what it does from naught to 180, no, 360, that is, of course. That was this 180 I just read out. Now, the interesting thing was to check the transformation formula. So I make a check which computes the original value and the value we have to check it against, and just print the difference. So the imaginary unit, that gives 10 to minus 16th. That's not really satisfactory. But alright, it's not far off. But then we check all with imaginary part 0.8 from minus 1.5 to 0.5. We divide it by 10, the counter by 10 here. And this agrees fairly well in the beginning. That's fine. Excellent. We're doing well. But then it starts becoming, well, it's directly significant here. But on the other hand, if we have a holomorphic function on H which agrees for a dense number of points here, then it's incomprehensible how it can start to diverge. But I have it here, it's 10 to minus 8th, that's a factor. That's like 12 orders of 12 or 10 orders of magnitude larger than I was prepared to accept. I don't really understand why that is. I checked the numerics somewhat and found no error, so I don't know what's happening here, why there's this deviation. So that was the numeric work. So let's assume for the time being that we have the right candidate and see if we can start doing some magic on this sum. I did spend some time working on another function that was a theta function from chapter 2. So the chi we used here, that was n over 3. It has a nice transformation formula. I don't quite remember it. It was something with I and t and maybe a number to minus 3/2, and then something like I square root 3. This is not the exact, and then of minus 1 divided by 9 theta. Something like that. So I wondered if we could construct a modular form from this. It's not quite impossible, but I haven't been able to make one in any of these MK spaces. So I spent like 1.5 afternoon working on this, but was not able to do anything about it. So where we are now is that I will try to see if I can do any work on this series. Now it's Friday, February the 16th, and I'll just report what I have done. I've been working a little on this function, trying to make a modular form out of it, whatever order 3 I think would be relevant to try, but I didn't manage to do it. What I have done is that I took this series, that is the coefficients, and entered into the encyclopedia of integer sequences. There we have it. And it spit out something that worries me a little. Offset, perhaps 2. Integer solutions to this guy. I can't really make that agree. If n is 0, it's 1, of course. If it's 1, then there are 6. That makes sense. If it's 2, we have 6 as well. And if it's 3, they must all be 1. So that gives 8 combinations. So I don't really see how that adds up to this. Well, one of the links led to this series, which is exactly, here we've got it, which is exactly the formula I found. And that's interesting. Coefficients of the Dedekind zeta function for the quadratic number field of discriminant minus 3. However, this series had also a note, or was it this one? A note on, I copied this, that the series was from Ramanujan's notebook, part 4. That confirms that we are dealing with really basic material in the field. And that's what I'll do next week. I will go to the library. And you can see when I get stuck it's a good idea to go to the library. So it's now Tuesday, February 20th. An update on the quest. I wasn't able to get anything sensible working on this function from chapter 2. Then I tried working on another function which should lead to this sum. But I wasn't able to, and that's where we sum overall n instead, to be able to use, now what is it called? To be able to use Poisson's formula. But that didn't give anything I could use for this project anyway. The next thing was studying this guy, which didn't give anything resembling what I was working with or anything I could convert to it. And the library, they didn't have the book I was looking for. So what I did was to ask a contact at the University of Copenhagen I have, and did you mean weight 1 on gamma naught 3? Yes, I did, but with chi of course, but that I didn't say that. That was implicitly understood, I think. He didn't understand it, so wasn't precise enough. So it says there are none, only the null function. But then he gave me a database, but that seems to be of cusp form, so I don't know what. They all started with Q, no constant term. And I said that, and then he wrote, if it's gamma 1, 3, then my first guess is that you have found an Eisenstein series of weight 1. And he said I should check this book, and I've ordered it. It will be coming within a week, and then I can see they should have a table where it is, and that would end my quest. Hello, this is now Friday the 8th of March. I bought the book and found the chapter on Eisenstein's series of weight 1, and there is an explicit construction that leads to this formula. Let us just, well, I can't move it, sorry, which leads to this function. There is a constant, and then 2 times the sum of, never mind, exactly the formula I have. So this should be like 1/3. I don't know how to compute this constant, but what I can conclude by now is that it's folklore, it exists. They didn't put it into the exercises, but I believe it's folklore that it may be computed. So this finishes my quest.